Hello, everyone. Good morning, good afternoon, and good evening to one and all here. Dear authors and invited guests, welcome to Technical Session 4E. Myself, Deepika Jain, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GIA Scholastic LLP, it is my great pleasure to welcome you to the second International Conference on Innovations in Biotechnology and Health Sciences, Biocom 2025, London, United Kingdom. The second edition of this conference has been organized in a hybrid mode. The physical event was held yesterday in London, and the virtual event is being held through Zoom, that is today. I hope you will enjoy the knowledgeable sessions throughout the day. In this session, we have 7 presentations. Each presenter will be given 12 minutes for their presentation and 3 minutes for any question and answers. On 10 minutes, I'll be raising a gentle reminder. I also request the participants that you stay with us till the closing remarks. And if you have any query, you can update to me in the chat box. Just before we start the session, I would like to introduce to our session chair, Dr. Madhurima Chopadhyay. I welcome you, ma'am.
Thank you.
Just
Good
a minute.
morning,
Sir,
everyone.
can you just stop? Just a minute.
Hello, audible?
Yes, ma'am, you're audible.
Good morning, all the
Good morning.
participants.
Good morning, everybody.
Just a minute. Dr. Madhurima Chotopadhyay is a professor and head of the Applied Electronics and Instrumentation Engineering Department at Heritage Institute of Technology. With extensive experience in teaching and research, she contributes significantly to the fields of applied electronics and instrumentation. I welcome you, ma'am. Thank you so much. Okay. Now I would like to start with the papers with our first presenter, Simon Fong. Are you here? Okay. Is there the presenter of the paper Efficient Cardiac Images Segmentation with Compressed Vision Transformers and Post-Training Quantitation are here? Are you here, ma'am? Asia?
Hello, yes, good morning.
Yes, are you
I'm
ready
here.
with the presentation?
Yeah, thank you. Good morning. First, I would like to present myself. My name is Asia Boukamla, a PhD student attributed to the LabJet laboratory at the University of Beji Mukhtar Hannaba of Algeria. Today, I will do a presentation course entitled Efficient Cardiac Image Segmentation with Compressed Vision Transformers and Post-Training Quantization. Let's begin by presenting the main points we will be focusing on today. First, we will start with an introduction to cardiovascular diseases. Next, we will explain the key concepts of the research subject. Then, we will present the proposed approach. After that, we will discuss the main findings of this work. And finally, we will conclude our presentation with perspectives and future work. Cardiovascular diseases are the leading cause of mortality worldwide, according to the World Health Organization. So early and accurate diagnosis is crucial, but often challenging due to the limitations of traditional diagnostic methods. This creates a demand for advanced non-invasive and automated solutions. Cardiovascular imaging has evolved as a critical tool in the identification and diagnosis of cardiovascular diseases. The application of artificial intelligence techniques to this area has recently piqued the interest of researchers due to their ability to automatically learn complex features from large volumes of medical image data. The integration of artificial intelligence or AI techniques into the process of building medical decision support systems improve diagnostic efficiency. Among these techniques, we have vision transformers that have gained significant attention for their ability to capture complex spatial dependencies in medical imaging. Vision transformers, or VITs, are a type of deep learning model that leverage the transformer architecture to process visual data. Instead of processing an image as a grid of pixels, VITs divide the image into small patches, flatten them, and process them as sequences of vectors. These patches are treated as tokens with positional embeddings added to preserve spatial information, enabling VITs to analyze both local and global patterns within the image. The self-attention mechanism in vision transformers is a key operation that determines how much focus each part of the input should receive. It relies heavily on linear algebra operations. So the formula for self-attention is defined as follows. The mechanism determines how important each input patch is to others, dynamically adjusting the focus. The softmax function ensures the attention weights are interpretable as probabilities. This formulation enables transformers to capture relationships between all patches in an image, regardless of their spatial distance. Vision transformers were initially adapted for image classification, where the goal is to assign a label to an entire image. Recently, VITs have been adapted to image segmentation tasks. So instead of predicting a single label, these models output a segmentation mask where the input image is divided into meaningful regions, such as identifying specific anatomical structures. For example, in this case, cardiac structures, which are the left ventricle, the right ventricle, and the myocardium. To adapt VITs for segmentation, researchers integrated decoder structures or hybrid architectures. We have TransUNet, SwinUNet, and SegFormer are three powerful VIT models specifically developed for medical image segmentation. Despite their effectiveness in medical image segmentation, VITs are computationally expensive and require significant memory, making deployment challenging for real-time applications. To address this, we explore post-training quantization as a method to reduce model complexity while maintaining segmentation accuracy. So post-training quantization is a technique applied after training to convert high precision models into low precision models, such as 8-bit integers. This process aims to reduce model size and computational requirements without significant loss in accuracy. The quantization process involves mapping real valued inputs to integer values using the function defined in the first equation, where R represents the real input value. The scaling factor S is crucial in this conversion and is calculated as defined in the second equation, with alpha and beta defining the clipping range. This ensures that the continuous range of real numbers is appropriately mapped to a discrete set of integer values, facilitating efficient computation. Post-training quantization includes three main techniques, which are float 16 quantization, which reduces model size and improves latency by converting floating 32 to float 16 numbers. Full integer quantization, which compresses models further by converting parameters to 8-bit integers with minimal accuracy loss. And dynamic range quantization, which adjusts weights and activations based on their value range to enhance efficiency. In this work, we investigate the impact of post-training quantization on compressing vision transformers for cardiac image segmentation. The proposed approach follows a structured pipeline. First, cardiac image MRI images undergo a pre-processing, including resizing, normalization, and region of interest extraction using a UNet model. The extracted region of interest is then fed into a VIT-based segmentation model, which is trained on the dataset. After training, a small calibration dataset is used to compute scaling factors and zero-point parameters for quantization. Finally, post-training quantization is applied to reduce model size while preserving segmentation accuracy. We use the ACDC dataset from the MICAI 2017 challenge, which consists of 3D short-axis sine MRI scans from 150 patients. For our experiments, we extracted 1,489 2D images from 100 3D volumes, focusing on the end diastolic and end systolic phases. The dataset provides expert annotated segmentation for the right ventricle, myocardium, and left ventricle structures of the heart, serving as ground truth. We split the data into 70%, 20%, and 10% for training, testing, and validation um, respectively, for validation, to ensure a balanced evaluation of our approach. So multiple metrics have been used to evaluate the performance of the proposed approach, including dissimilarity coefficient, Hausdorff distance, average symmetric surface distance, and intersection over union. In the end diastolic phase in Table 1, float 16 quantization consistently outperforms full integer and dynamic range quantization. Across K metrics, which are DICE, Hausdorff distance, ASSD, and IUU, which is intersection over union. In the ES or end systolic phase in Table 2, we can see that this is confirmed by the results in the end systolic phase, with float 16 quantization outperforming other techniques in segmentation precision. For TransUNet, float 16 achieves a DICE score of 0.987 and a Hausdorff distance of 16.158, slightly better than full integer and dynamic range quantization. Overall, float 16 quantization enhances segmentation boundaries, especially in right ventricle segmentation, with significant improvements in Hausdorff distance and ASSD values, balancing accuracy and efficiency. To assess the computational efficiency of VIT models, both prior and following quantization, we analyze metrics such as the number of parameters, model size in megabytes, compression rate, and inference time, which is here presented as latency. So in table 3 shows the performance of models before and after applying 3 quantization techniques during the end diastolic phase. Overall, float 16 quantization outperforms full integer and dynamic range quantization in segmentation performance, achieving higher or similar DICE scores and better boundary precision. This balance between reduced model complexity and high segmentation
Dear
quality
presenter, you have 2 minutes left.
Okay, thank you so much. The following figure illustrates the segmentation performance of VIT models during the end diastolic phase, both with and without quantization. The circle size corresponding to the ASSD distance, and the circle color reflecting the Hausdorff distance value. The ablation study is conducted by analyzing the performance of VIT models with and without the integration of this technique. Tables 4 and 5 provide the experimental data demonstrating minimal variation in segmentation accuracy, confirming that the effectiveness of float 16 quantization in reducing complexity without sacrificing performance. So float 16 quantization had minimal impact on segmentation accuracy across all VIT models, with only slight variations in DICE, IUU, and HD metrics. TransUNet maintained high segmentation performance in both end diastolic and end systolic phases, with a DICE value of 0.89 and 0.98 and 0.987 respectively. Its boundary segmentation remains stable, confirming its robustness in quantization. The following figure is a visualization of the segmentation results of different VIT models during the end diastole phase. the evaluation showed that float 16 quantization achieves an optimal between model compression and segmentation accuracy, outperforming full integer and dynamic range quantization. TransUnit demonstrated the most robust performance, effectively leveraging both CNN-based spatial localization and VIT-based global context for precise cardiac segmentation. We conclude that quantization-based compression effectively optimizes VIT models for cardiac MR image segmentation, reducing size and computation while maintaining accuracy. And floating 16 quantization minimizes latency and storage needs, making it suitable for resource-constrained settings. Thank you for your attention.
Thank you. Thank you for the presentation. Any
Thank
questions,
you.
ma'am?
Hello, Ashia.
Hi, hello.
Hello, you have a very nice presentation.
Ma'am, your voice is not so loud.
Hello.
Hi. We can hear you now. Thank you.
Hello, Ashia. Can you
Yeah.
hear me?
Yeah, I can hear you.
Okay. So we have presented nicely about your vision transformers instead of CNN. Now I have one question that
Yeah.
how the resolution of the image will affect, or the resolution of the segmented image will affect
Yeah.
if you decreases the quantization from 32-bit to 8-bit.
Okay, thank you for your question. So when we say the quantization reduces the precision from 32 floating 32 to, for example, floating 16 or to 8-bit, we are here talking about the weights and the activation functions. You can hear me? Yeah, we reduce the size in which a weight or an activation function is stored on the memory. I don't know
Okay.
if you hear me. Yeah.
Okay, that gives you that is beneficial for
Yeah.
the software.
So we are reducing the computations on the memory, you know,
Okay, but will
and
it affect resolution in any way? Resolution?
the resolution of the images, you can say.
Yes, yes.
You can see here the resolution of the images. It's not really affected by the quantized models. TransUnit, SwinUnit, and SegFormer here are quantized models. We only compare their performance between each other. You see,
Yes.
you can see the difference with the ground truth. There is no really difference between.
So this resolution thing you have not now studied, I think.
Sorry, I couldn't
The
hear you.
resolution part you have not yet studied, I think. You have studied accuracy, precision, all this.
You mean this table and this figure?
You studied accuracy, you told that it gives very good precision and all. So resolution you should study in the next time, I think. It may work out. Okay.
Thank you so much. Thank you so much. Yeah.
Thank you.
Thank you.
Thank you. Thank you, ma'am. So we have our next presenter with us.
Yes, good day, everyone. First of all, I will start. May I speak?
Just a minute, sir. Would be presenting a paper on machine learning for myocardial infarction detection in ECG signals, the influence of the image background. Yes, sir. Can you just share your screen, please?
Yes. Okay. So I presume I can start sharing.
Yes, please.
Good day, everyone. I'm Rusu Cristinel Gabriel. I'm a PhD student at Dunărea de Jos University of Galați, the Modeling and Simulating Laboratory of Science faculty. Today, I will be presented our work on machine learning for myocardial infarction detection in ECG signals, specifically focusing on the influence of the image background on classification accuracy. This research aims to improve the detection of myocardial infarction from ECG signals using machine learning, a tool that has shown impressive results in medical diagnosis.
Sir, you can move your slides also.
Yes. Cardiovascular diseases are the leading cause of global mortality, responsible for nearly 18 million deaths annually, with this number expected to rise significantly in the coming decades. Among these diseases, myocardial infarction is a primary concern. Electrocardiograms have long been used to assess heart condition, but despite their value, ECG signals alone are not always sufficient for accurate myocardial infarction prediction. Problems arise due to various factors, such as artifacts in the ECG images, including background lines from paper-based ECGs that can obscure the essential heart activity data. Motivation of the study. Our study aims to understand whether removing these background lines can improve the accuracy of myocardial detection using machine learning. Machine learning has already shown promise in automating the classification of ECG signals.
Sorry for the interruption. It is still on the first slideshow. Your pages are not
It's
moving, sir.
research motivation is different. Isn't changing.
No, sir.
Just a second. So I'll share.
You can just stop and yeah, I can see it now. Research objective.
Yes, I guess it's okay.
Yes, sir. You can continue.
Okay. So, research objective. The object of our work is explore how background removal impacts the performance of 6 different machine learning classifiers in detecting machine learning from ECG signals. We are using both raw ECG images with background lines and clear images with the background removed to train and evaluate the models. Dataset and pre-processing. We use ECG data from 488 subjects, of which 248 of myocardial infarction and 240 healthy subjects. The data was pre-processed to focus on the first lead limb ECG signal, which simplifies the computation while retaining critical information for myocardial infarction detection. We also used data augmentation to ensure a balanced data set and prevent overfitting. The images were resized to 499 per 300 pixels for consistency. Background removal. The issue of background interference in ECG images is significant. Grid lines and colored artifacts can confuse the classifier. To address this, we use Otsu threshold method, which effectively removes background lines without degrading the ECG signal itself. The comparison between raw ECG images and clear ECG images demonstrates the effectiveness of this approach. As you can see, we rotate by 40 degrees the images to augmentate data. So we implemented 6 different machine learning models for this classification task. We use ADA Boost, Gaussian naive Bayes, K nearest neighbors, quadratic discriminant analysis, random forest, support vector machine. The features used by the models include entropy and energy measures, which capture important aspects of the ECG signals that are useful for distinguishing between normal and myocardial infarction signals. These features were extracted using a wavelet transfer and include metrics such as Shannon entropy and log entropy, which quantify the complexity of information content of the signals. As for results, The results were quite revealing when tested on raw images with background lines. The models shown vary levels of accuracy, but overall the accuracy was reduced due to background interference. In contrast, when the models were trained and tested on clear ECG images, we observed significant improvements. ADA Boost achieved 32.1 higher accuracy, KNN showed 27.3 improvement, Random Forest showed 18.5 improvement. The models trained on clear ECG images perform significant better, with ADA Boost, KNN, and RF achieving over 97% of accuracy. Support vector machine also showed an impressive improvement of 66.4 when background lines were removed. Performance metrics. We evaluate the models using several performance metrics, such as accuracy, precision, recall, F1 score, and then the F1 score of the best performing models, ADA Boost, KNN, and Random Forest were particularly high, indicating that these models are both precise and robust in distinguishing between healthy and myocardial infarction signals. For conclusion, our study confirms that removing background artifacts from ECG images significantly improves the performance of machine learning models in detecting myocardial infarction. Among the models tested, ADA Boost, KNN, and Random Forest provided the best results, with accuracy of over 97% when trained on clear data. This work paves the way for more accurate and efficient AI-based tool for myocardial infarction detection, which could help in early diagnosis and reduce the human error in clinical settings. As for future work, moving forward, we plan to expand the data sets to improve the generalization of our models. Additionally, we aim to explore the application of deep learning models to further enhance ECG classification accuracy. We also intend to test our model on other ECG data sets to validate their robustness. Acknowledgements. This research is part of Melchior project funded under PNCDY 4th European and International Cooperation Program. We also thank the contribution of the Pervez Elahi Institute of Cardiology, Multan, Pakistan, and Mandley for providing the ECG datasets. Thank you for your attention. I'm happy to answer any question you might have.
Thank you for the presentation. Any questions, ma'am?
Hello.
Hello.
Sanan. Hello, you have presented a comparison study among 6 different classifiers.
Yes.
And finally, you have studied the accuracy, precision, recall, and FI score of all these classifiers and found that 3 classifiers gave very good results for clear images. That was a very good observation.
Thank you.
I have one question, that what are the high-level features provided by 12 lead ECG signals, as you mentioned?
We choose the first lead limb to analyze how background removal increase our performance. We haven't studies for all 12 leads. We found that first lead limb is most significant, but as you know from cardiology, first and second refers to anterior heart, and third, fourth, and fifth to posterior heart. So our study was only about first lead limb.
Okay, thank you.
You're welcome.
Thank you. We have our next presenter with us who will be presenting a paper on management of informatiology processes in medicine and health tourism. Yes, sir. Alexander Latkai, are you here?
Yes, good morning.
Yes, sir. Good morning. You can start sharing your screen, please.
Thank you. I try to share with my screen. One moment.
Yes.
Okay, can you see this?
Yes, I can.
Okay, very well. We have informatiology processes in medicine and health tourism. This report was prepared by a co-author from different universities from Ukraine, Vladimir Kilivnik, Alexander Gledky, Alexander Getsi, etc., etc. It's different universities from Kiev, from Vinnytsia, Kharkiv, and other regions and other cities of Ukraine. Can you see next picture?
Yes, I can see.
Is it okay? Okay, very well. For optimal decision-making in the management of informatiology processes in medicine and health tourism, it's important to examine all information about the patients received from all sources. In this case, the functional conditions of the sensory system of both the patient and the doctor is critical. So in the figure 1, you can see a structured model of the body information resources. Information resources of human body. You can see different components of these resources of human memory, of reception systems, on sensor system, on conduction system, system of information use, system of information management or monitoring, and system of information use control. With different arrows that show relations between these different parts of structure model and information resources of human body. Information processes occurring in the human body are presented in figure 2. You can see such elements as information accumulation in human memory, information perception, information transfer, information use, and monitoring. So this figure looks like the first one, but it's showing some information that all information processes occurring in the body are supported by appropriate information resources. On the next picture, we can see a mechanism of information accumulation in human memory. We can see human memory and different arrows with efferent starts, decision-making, efferent system, synthesis, behavior result in action, result receptor, result parameter, receptor of behavior result in action, and efferent synthesis that back to human memory. This is informatiology model of information accumulation in human memory. In the next picture, we have general principles of building the body functional systems that include activity results, hierarchy of systems, self-regulation, multi-correlation of final results, isomorphism of systems, system genesis, and selectivity, and iteration for achievement results. This is a structural model of building principles of human body functional system. In figure 5, you can see an informatiology model of human body functional system that include useful adaptive results, reception of the results, reverse explanation, central architecture of nervous system analyzers, and also performance components: somatic, vegetative, endocrine, behavior, maybe someone else. That's why the adaptive results useful for the organism as the main system forming factor is the leading one in the functional system general theory. The informatiology model of the formation of human activity, adaptive results, is shown on the figure 6. You can see this informatiology model with dominant need and non-dominant need in the opposite side, and with different components. For example, maintenance of homeostasis in human body, results of behavior activity, and results of social activity. So this informatiology model show different types of human activities and show different forming factors in the functional systems of human body. And next, on the next picture, we have natural information systems. Function is in compliance with the universal structure and functional model of the information systems. They, like other information systems, have their own information processes, IP, and information resources, IO. So figure 7 shows a structural model of the natural information systems that include information processes and information resources. For example, self-information, genetics of the universe, information events, energy biological processes that include into IP information processes, and some one of them are included into information resources. Energy biological resources, informatiology laws, and knowledge in human memory. What about artificial information system? Artificial information systems are divided on information processes and information resources also. Artificial information processes include correlation model with natural IP, information processes and phenomena, box, and energy biological processes. Artificial information processes include energy biological technologies and resources, informatiology laws, and artificial intelligence systems. So you can see figure 8 that shows structured model of artificial information system. You can see the same boxes and information processes, information resources, and different correlation of artificial processes with natural one, information processes and phenomena, energy biological processes, etc. And figure 9 shows informatiology resources of artificial information systems. These informatiology resources are divided on 3 parts: information in books and other information sources. For example, electronic sources, unified global information cell space, and artificial intelligence that is very popular nowadays. So this is informational resources of artificial nature. And the structure of informational technologies in artificial information systems is shown in figure. Informatiology technologies include informatiology computer technologies, informatics, cybernetics, and informatiology energy biologic technologies. These elements of artificial information systems we can use in health treatment, in health tourism, in different elements of human body recovering, not only on specific physical level, but also on mental level. And we have different investigations concerning influence of wellness therapy on artificial level, and maybe climate therapy on internet on this level. And For example, we try to use 4 methods of diagnostics and treatment. It's also include informatics and cybernetic systems for treatment of human body. So these elements become one of the main information systems for usage in medicine and health tourism. Thank you very much.
Yes, sir. Thank you. Any questions, ma'am?
Yes, it is very nice and interesting presentation. I have just one small question. That what are the key principles of the human body functional system structural model proposed in this study? I want to know what are the key principles of the human body functional system.
Repeat, please. I can't understand. Please repeat.
Should I repeat?
Repeat, please.
What are the key principles of the human body functional system structural model proposed in this particular study? I want to know what are the key principles that you have to follow when you are doing this human body functional system structural model. Any principles have you followed or taken care of? Any short explanation or anything?
We try to analyze that different information and collected in human existence, in human body existence, are useful for treatment. And we can use this information collected using different artificial intelligence programs or devices, or maybe Internet of Things, or maybe some other one. We try to collect them, systemize them, and try to use for treatment on the information level. So, for example, 4 methods show us positive trends of treatment of different diseases using information system. These methods collect different information things from human mind or from human body and try to improve them firstly using information received from these different receptors. That's why we try to show these methods for usage in medicine, in spa, for example, in different human recovery of human body.
Okay. Thank you. Thank you.
Thank you very much.
Thank you for the presentation. Thank you.
Thank you very much.
Thank you. We have our next presenter with us, who would be presenting a paper on. Who would be presenting? Can you hear me?
Hello.
Yeah. Sorry, I lost my connection. Yes.
I'm back.
Yeah, you would be. We have our next presenter with us who would be presenting a paper on novel integrated approach for early detection of Asperger's syndrome using machine learning. Niyantara Mohan Babu, are you here?
Yes, I'm here.
You can start sharing your screen, please.
Okay, thank you. Okay, can you see my screen?
Yes, I can.
Okay, thank you. I'll begin now. Okay, so good morning, everyone. My name is Nyantra. I am a high school student from the United States, and I have worked with K. Vijayan and Alekia Devi Malipati to create a novel integrated approach for the early detection of Asperger's syndrome using machine learning. So we're going to first go over the difference between autism and Asperger's syndrome. So autism spectrum disorder has very mild to very severe symptoms, and it has a wide range of issues. So, for example, the intelligence has high variance, while Asperger's syndrome has milder symptoms, and the intelligence is usually average or above average. So Asperger's syndrome fits under autism spectrum disorder as a milder version, and often children with Asperger's syndrome seem more neurotypical. So there are many different approaches to the diagnosis of autism. For example, there's facial image processing, which goes over the facial structure of the children with autism spectrum disorder or Asperger's, and it tries to diagnose based on their facial structure. Same for gaze point tracking, like it goes over their eye movements and tries to diagnose based on that. The QChat questionnaire diagnoses based on a list of questions provided to the parents, and they rank each of, it'll be explained more in detail later, but they basically rank each of the questions from a scale of 1 to 5. So current research focuses on only one particular symptom or area of diagnosis, but this may not successfully detect ASD in children with high functioning autism or Asperger's syndrome. So for example, in image processing based detection, some children can look neurotypical unless they're placed in a certain social situation. Same thing with detection based on gaze points. Children may not have an irregularity in eye movement that is shown until they're placed in like a social situation. The use of questionnaires can be limited by the knowledge of the parents, or there may be a bias present. The parent may not want to say that their child has autism. So, if no two children can produce the same symptoms, how can we use only one method for detection? That is where the novel integrated approach comes in. So, individuals with high functioning autism or Asperger's syndrome are hard to detect with a single method of detection. So, this single data point can lead to a wrong diagnosis or inaccuracy. So, we use an integrated approach which combines image processing, eye tracking, and questionnaires with machine learning. Our algorithm uses a vote-based decision, which means if any of the models detect autism, then the individual is proven to have autism spectrum disorder. This innovative approach can improve the accuracy and accessibility of ASD detection and can lead to widespread early intervention and care. So for the image processing model, I use the CNN VGD16 model, which is a convolutional neural network, and it is an example of supervised learning, which means that images that have already been identified are fed into the model for training. So we use both autistic and non-autistic images, and there are around 2,450 training images, and there are test images. So these images are shuffled and used for training, and the convolutional neural network layers are frozen, and only the dense layers are altered. And we use binary regression to categorize the children as autistic or non-autistic. And in this model, we ran through 100 epochs. So next, we'll go over the model performance. So our overall accuracy had an upward sloping curve, and it reached 73% accuracy. And we faced some noise around 15 to 17 epochs due to certain limitations in the dataset. So next, we'll go over the eye tracking model, which used a random forest classifier, and it categorized whether the data is autistic or non-autistic using the decision nodes. And then we identified target variables and labels from the data set. So this approach is much more accurate than the decision tree approach. And on the right, you can see many different data points that we used. So the model performance for this one, we calculated the model performance for different tree depths and different amounts of trees as well. So as you can see, the single decision tree and 10 decision trees had a lower accuracy than the 100 decision trees, and we reached an accuracy of 70% on this model. Now we continue on to the QChat 10 questionnaire, which we used a neural network, a multi-layer perceptron for this one. So for the QChat 10 questionnaire, there are 10 questions, such as, does your child look at you when you call his or her name? Or how easy is it for you to make eye contact with your child? And the parents or primary caregiver rank these questions from 1 to 5. And as we see, and then this also, like, as this model, as well as taking the QChat score, also takes the age, ethnicity, family history, and presence of jaundice, and it takes into consideration the other factors. So it's aimed at toddlers and younger children, and is filled by a parent or primary caregiver. So as we see for the QChat, there is a higher true positive rate than there is a false positive rate, and there is a higher true negative rate than there is a false negative rate. So the combination of all three of these models come together in our novel integrated approach. So we combine image processing, eye tracking, and the QChat questionnaire, and we end with a diagnosis for autism. If the person's data triggers even one of the three models, there's a chance that they're autistic and should continue on to further testing. So next we test this integrated approach, and we test it using synthetic data from the combinations of the three data sets. So the probabilities of whether they're autistic or not autistic are converted to binary predictions using a threshold of 0.5. The code iterates over the data points, and it combines the predictions of the three models. If any of the models say that the child is autistic, then the data is classified as autistic. Otherwise, it is classified as non-autistic. And this approach combines predictions from multiple models to make a final decision, which can help in accuracy and robustness of the classification. So let's see how the integration of multiple models can help increase accuracy. So we have taken 5 examples, like 5 sample data sets. And as you can see, each of the individual models may have had inaccuracies in detection, but the overall integrated approach has shown a 100% accuracy in this example. So for example, we can take test data 1, and for the image processing, it's predicted that the data is non-autistic. Same thing for the eye tracking. It says the data is non-autistic. The QChat is the only one that predicted that the data shows an autistic child, which is true. But when we combine all 3 of these models, then we get the correct data that the child is autistic. And this is again shown with test data 3 and test data 4. So there may be opportunities for future research. In this model, we have used image processing, eye tracking, and QChat questionnaire, but we may also use other diagnostic methods such as MRI scans. We can also increase the sample size or the amount of data for each data model, or we can use stronger or more powerful models. Another alternative is to use a single multimodal architecture as opposed to 3 different models. Thank you. That's everything. Any questions?
Thank you. Any questions, ma'am?
First of all, I want to congratulate Niyantra. As a high school student, you have presented so nicely and you have done
Thank you.
wonderful, commendable job work.
Thank you for
So I have
thank you for
one
coming.
small questions to you. That is, I have one question, that how might this novel integrated approach to ASD detection improve the early identification and intervention for individuals with autism?
Okay, so I'll just go back to this slide. So basically, like how I said before, is that certain detection methods they can be inaccurate, or they can have like for example, if a child that has Asperger's syndrome has very normal eye tracking, then they won't be detected as having Asperger's or autism. So they cannot get the help that they need at that time. Like they cannot get certain programs, or they cannot go into therapy because they do not know that they have Asperger's or autism. So that is why our integrated approach leverages different methods. Like, for example, if they do not have any discrepancies in eye tracking, then they can have differences in image processing, or they can have differences in QChat. So that's why we use the multiple approach to have a more accurate diagnosis that can lead to a better possible intervention.
Yes, that I understood, but I am asking that
Yeah.
suppose a child having such autism, so
Mm-hmm.
instead of going to doctor, if you use your model, which one is the earliest detection?
Like, which one is the most accurate?
Earliest detection. Suppose if a child has autism.
Yes.
Okay, so with his eyeball movement or other gesture, people can find he or she may have autism. But by applying this model, can we get confirmation that it is 100% or percentage type? Can it be detected in that sense?
I don't get what you mean. So are you saying that the model will detect if they have autism?
I'm asking how much your model is affected to
Oh,
detect
okay.
the percentage of autism like that.
So the overall accuracy, we have reached 70%. So it should be able to detect accurately whether they have autism or not.
Okay, thank you.
Thank you. And thank you for the comments. Like, it really made me like happy.
Thank you. Thank you.
Best wishes for your future.
Thank you so much, ma'am.
Okay, so we'll move on to our next presentation. We have our next presenter who would be presenting a paper on synchronization of life sciences with data science, the roles of big data analytics. Do we have the presenter of this paper here?
Yeah, I am here. Let me share my paper.
Yes, sir.
But I'm not okay.
Please share your screen.
Okay. Can you see my screen now?
Yes, sir. But there is some background music going on.
Oh, let me off it. I'm very sorry for that. Okay.
Yes, so you can start with your presentation.
Okay. Well, good morning, everyone. I am Dr. Rotimi Williams Bello from Swan University of Technology, South Africa. It gladdens my heart to be one of the presenters this morning. I will be here presenting on synchronization. It's all about the association between data science and big data. What are the roles of these two things as it affects each sector? Recently, the information released has it that the current world population has the previous population, and more than 2/3 of the population have access to the internet. Moreover, billions of various mobile devices owned by individuals contribute to the enormous data generation and proliferation. The life sciences permeate so many aspects of our individual lives, from our environment to our health care, and to a discourse about stem cell research and genetic testing. Therefore, there is a need to model these skills through big data integration, whereby the model evolvement and development will facilitate feasible prediction for individuals. We believe that while spectacular science have been made and witnessed in recent decades, so much remains unknown in the field of life sciences. Moreover, it is very, very difficult to convince and train individuals with little or no knowledge of data science to accept big data, whether for decision-making on the part of the healthcare providers or privacy assurance on the part of patients. It is on this note that we present this objective as follows: to synchronize life science with data science using big data analytics in order to improve healthcare services and aggregate increasing information surrounding the multiple scales for what constitutes a disease. We have big data analytics and healthcare as the engine of this, and we look at challenges of big data, increasing complexity of healthcare data, enhanced healthcare delivery with big data, and benefit of healthcare analytic data. If you look at my figure 1, this figure illustrates a simple portal platform for healthcare services. It is a platform developed for patients that do not have the privilege to move from one location to another. You know, under some emergencies, when a patient is in need of immediate healthcare attention, and there is no way to trace such a patient history, it will be so difficult for such a patient to receive medical attention appropriately. So with this platform developed, it is very easy for a patient to get immediate medical attention from any doctor all over the world by just linking to the portal and retrieve anything that has to do with the history of such a patient. And don't forget that the history and the database containing the history of these patients is what we collect together, and we name it analytic data and big data. The material and method that we use in processing big data, or that can be used to process big data, are the data that are containing and a collection of a vast amount of medical data, clinical data, behavioral data, various measurements, statistical data, financial data, insurance data, demographic of specific population, to mention just a few, collected from various healthcare data sources. Medical or clinical data are beginning to be digitalized to include medical images, structured electronic health records, and unstructured electronic health records. This is slightly different from behavioral data that comprises mobility sensor data, physical activity data, sleep patterns data, dietary habit data, stress level data, social interaction data, and adherence to medical treatments data. Open source platforms such as MapReduce and Hadoop platform, which are Java-based framework that achieves the application of big data analytics in healthcare for storage management and large data processing for applications. These are all the things that we put together as a material that we know that is good for processing big data. The material continues. If you look at the figure 2 very carefully, you will see this is a channel that is a middleman between a doctor and the patients. We try to make this as part of our design to ensure that there is data security. Yes, that information about each patient is secured and is between their providers, their health providers, and they that we call the patients, so that anybody cannot just without authentication enter into the platform and get some private information about such a patient, which they might use to their disadvantage in the social gathering. Now, other open source solutions for big data in healthcare are the tools and systems for visualizing healthcare applications, optimization techniques of quality of service for big data healthcare applications, and security and privacy preservation techniques for healthcare information. The tools used in big data are Hadoop, which I've said earlier on, which aids data storage and analysis. MongoDB, which is applied on flexible data sets. We have Talent, which is used to integrating and managing data. Cassandra, which is distributed database utilized for handling chunks of data. This is the experiment result that we carried out we collected data from one of the federal hospitals in our country. We program it for individual patients in order to make sure that a patient, wherever he gets to, is able to get the medical attention that such a patient needed. There is no restriction that, oh, you are in another location, your histories are not with us. Such hospital can one way or the other contact the primary provider, healthcare provider of such a patient, and they will be able to continue from wherever the medical attention need to continue from. If you see the figure is a patient referral record with the details, medical details of such a patient to make it easy for the doctor at the other end to continue medical as the case may be. The benefit of big data analytics are patient outcome improvement, reduction in cost, personalized treatment, telemedicine, real-time alert, electronic health records. And the roles of healthcare provider in data-driven decision-making are as follows: data analysis, treatment plans development, identification of at-risk patients, monitoring quality of care, and identification of areas that need improvement. C, potential barrier to big data. You know, I have said earlier on that big data, as it is a collection of data from different sources in order to make decision on individual tasks easy, we still have to talk about the barriers that confront it. We have security of the data, the quality of data, the specialized skills. Other likely barrier is language barrier, and finally, the regulatory compliance. D, we talk about the compliance of big data tools with HIPAA regulation, which is the tools of big data to comply with HIPAA as follows: exclusion and access control. We will see the picture or the figure ahead. Auditing and patient consent, business associate agreement, backup and disaster recovery and risk assessment implementation, continuous training of employees, that is the healthcare providers, the professionals, and the workers. Here is the continuation of the discussion, as I said earlier on, for the figure 4
Dear
and 5.
presenter, you have 2 minutes left.
Okay, if you look at these pictures or figures, you will see that they were encrypted. They were encrypted, meaning that if anybody that doesn't have the authentication access for the accessing of this thing, if they access it, they are going to download what they cannot interpret. You can see that these things are not interpretable, they are encrypted. That is what we did to the individual data store or the individual patient's repository. Conclusion: in this paper, we have presented big data analytics in synchronizing life science with data science. We believe that big data has revolutionized healthcare delivery by healthcare providers through the adoption of modern tools and techniques that aid in understanding and interpreting clinical data set and research for informed decisions. These tools include Hadoop, Talent, etc., etc. With Hadoop, healthcare providers can easily actualize their goals by making operative data-driven services available to patients, which can also assist in predicting the needs of those patients. Big data is in a state of great intensity, with the vision of transforming the world healthcare delivery using state-of-the-art data analytic techniques. If the right tools and techniques can be provided for computation of big data, we believe that such acts will raise and arouse their impact in analyzing and interpreting large amounts of healthcare data sets, in addition to the required solution. Thank you, everyone.
Thank you. Any questions, ma'am?
Thank you for such a nice presentation. It is very important these days. I have one question, that what challenges exist in integrating big data for decision making in healthcare?
Yeah, I have said it earlier on. The greatest challenges confronting healthcare professionals using big data is that many of them do not want to agree that they need to be trained on how to be using big data. You know, it is not easy to tell a consultant of medicine that you need to be taught by some other professionals on how to use this particular technology. They feel that no, in our profession, we have been practicing this for ages. So you don't need to tell us how to manage big data. In fact, they will not even accept that there is something we call big data. And to the patient also, they will be arguing that no, we don't want our information to be shared, because sharing our information, we don't have the guarantee that it will be secured. You are lying to us. There is no protection law that will guide the data that we are submitting to you. So these are the little things that confronting big data analytics being spread into X sector. Thank you.
Thank you.
We have our next presenter with us who would be presenting a paper on transfer learning techniques for efficient deep neural networks in real-time strawberry freshness evolution.
Yes,
Alaya
ma'am.
Parveen, are you here?
Yes, ma'am.
Yes, you can start sharing your screen, please. Yes, please, you can start.
Hello, this is Alo from Daffodil International University, Department of CSC. Today, I'll be presenting our research on transfer learning techniques for efficient deep neural networks in real-time strawberry freshness evolution. Okay, in this presentation, I will discuss the motivation for this study, the challenges we face, the solution we implemented using transfer learning, and the results that demonstrate its effectiveness. Let's begin by looking at the abstract of our paper. As freshness is a crucial factor of determining the quality of strawberries in the food industry, especially for fruits like strawberries that are highly perishable, it's essential to assess freshness in real time to guarantee quality. Traditional methods for this, such as visual inspections, are not only time consuming but also subjective and inconsistent. So in this study, we applied transfer learning techniques which include pre-trained deep neural networks to assess strawberry freshness. This method allows us to avoid the high cost of building a neural networks from scratch and speeds up the training process significantly. Among the models, we tested the exception model performed the best, showing superior accuracy, precision, recall, and F1 score compared to other models. This indicates that exception is highly reliable for real-time strawberry freshness assessment. The research concludes that transfer learning is an efficient and cost-effective solution to determining the freshness of fruit in real time, saving both time and resources. In the introduction part, mainly we have investigates how deep learning and transfer learning models can be used to evaluate the freshness of strawberries, which is crucial for quality assurance in food markets. Let's talk about the problem statement. As we mentioned, strawberries are one of the most popular fruits worldwide, but they have a very short shelf life, making them prone to spoilage and physical damage after harvest. Freshness is critical in ensuring the fruit remains marketable and safe for consumption. However, the methods existing like freshness, such as inspection, are not reliable for large scale and real time applications. The challenges of subjective evaluation and the lack of comprehensive datasets make it difficult for current models to accurately classify strawberries as fresh or spoiled. This leads to inconsistency in freshness classification and can ultimately result in poor consumer experience for financial losses. So, to tackle these problems, we have some solutions. We decided to explore deep learning models, especially transfer learning. Transfer learning allows us to pre-train models and apply them to our specific task. This approach is much faster and more cost-effective than training a model from scratch, which requires large amount of data and computational resources. In this research, we applied several state-of-the-art deep learning models, including Inception V3, MobileNet V3, etc. These models were chosen because of their success in image classification tasks. We used a real-time system architecture which integrates high-resolution cameras and machine vision to assess strawberry freshness by evaluating their color, shape, and texture. In this section, I have highlighted some of the related work in the field of fruit freshness classification and detection. Like several studies have explored methods for fruit freshness detections. CNNs have shown to outperform traditional techniques like SVM by achieving higher accuracy through features like color and texture. Transfer learning models such as Inception V3 and GoogleNet, which use pre-trained networks, have proven effective for fruit quality classification, improving both accuracy and efficiency. Our research builds on these advancements to apply transfer learning for real-time freshness evaluations. Now let's discuss the dataset we used. Our dataset consists of images of strawberries specially captured to assess their freshness. The original dataset included over 600 images of fresh and rotten strawberries captured with high-resolution cameras. However, the high resolution of this image made it difficult to train models efficiency. So we resized the images to 448 into 448 pixels to reduce the training time. Additionally, we rescaled the images to adjust their pixel range to 0, 1, which is essential for neural network training. Since the original dataset was relatively small, we applied data augmentation techniques like rotation and horizontal flipping to artificially increase their size of the dataset. This helped improve the generalization to ability of the model and prevented overfitting. With the data pre-processed and augmented, we are ready to test various transfer learning models. Now, let's look at the architecture of the real-time freshness evaluation system that we have implemented. Our system works by recording video footage of strawberries in real time. The video is when processed and used for image extraction, where we extract frames that are analyzed for freshness detections. The extracted images are fed into a deep neural network model, which has been trained to recognize fresh and rotten strawberries based on visual features. The deep learning model used in our system is designed to identify key indicators of strawberry freshness such as color and textures. Once the model processes the images, it outputs a classification result, whether the strawberry is fresh or rotten. After this, the system goes through an end process where the results are sent to the relevant authorities such as storage managers to farmers to inform them in a real time. We have used these tested transfer learning models. We tested several transfer learning models, including Inception V3, Inception ResNet V2, MobileNet V2, NestNet MobileNet, and Exception. These models are well known for their ability to capture complex patterns in images. For example, the Inception V3 models uses parallel convolutional layers with different filter sizes to capture both local and global patterns in the image, which makes it great at handling complex image data. On the other hand, we uses depth-wise separable convolutions, which allows the model to extract features more efficiently while keeping computational cost low. This makes it ideal for real-time applications like the one we are targeting. We fine-tune these models with our strawberry dataset, test their performance in classifying strawberries as fresh or rotten. The model were trained, validated, and tested on both the original and augmented dataset. This is the implementation part. We have tried our original and augmented dataset. Let's take a look at the results. Initially, we tested the models on the original dataset. The exception model performed the best with the accuracy 92.38%, while the other model ranged from 80 to 90%. To improve performance, we then tested the model on the augmented dataset. The result was impressive. Exception achieved a remarkable accuracy around 99.33%. This indicates that the model not only improved significantly, but also demonstrated the higher precision recall and F1 score among the tested models. The confusion matrix shown here confirms that the exception model accurately distinguishes between fresh and rotten strawberries with minimal false positive and negatives. These results validate the effectiveness of transfer learning, especially when applied to real-time freshness evaluation system, saving time and computational resources. Okay, to conclude, transfer learning models, particularly exception, have shown great promise in real-time strawberry freshness evaluation. By applying pre-trained models and data augmentation, we are able to achieve high accuracy and build a real-time monitoring system. The exception model performed the best, achieving 99.33 accuracy on the augmented dataset, and it was chosen as the model for our real-time system. Moving forward, we plan to deploy this system as a mobile application, which will further improve accessibility and performance by enabling farmers, store managers, and retailers to monitor strawberry freshness in real time. Thank you.
Thank you. Thank you. Any questions, ma'am?
Hello, Alo, very nicely presented your work.
Thank you, ma'am.
I have just one observation that there is a 5% accuracy degrades while you are taking the trend data from validate one, isn't it?
Yeah.
So what is the reason?
Sorry, ma'am.
What is the reason? Why
Reason?
it's coming down while we are validating the accuracy?
Can you repeat the question?
Question is that you have shown two types of accuracy. One is the training accuracy. Another one is validation accuracy. While you are validating the data, it is 5% less, no? Accuracy is 5% less.
Yes.
Compared to the trend data. So while we are validating, why 5% is actually coming down, why the accuracy is less? That's my question. Have you find out the reason?
Maybe our model was overfitting on the training data, meaning it learns patterns who specifically from the training set and does not generalize well on unseen validation data.
5% may vary, 5 to 10% may vary. And I have one query. Can you use this model for knowing the freshness of other fruits like mango or apple?
Yes, ma'am.
For other fruits also we can use the same model.
Yes, ma'am.
Okay. Thank you.
Thank you, ma'am.
Thank you. Thank you. Okay, so we have come to the end of the session here. I sincerely thank our authors for their excellent presentation and contribution in this session, and all our participants for being a part of this international conference. I hope this session was informative enough. I, on behalf of the whole team, thank you for the support during the second version and the previous version of this conference. We will be happy to see you in the third version as well. All the presenters would be getting their digital certificates through email within 2 working days. All the papers have already been forwarded to the Springer board as well. And the publication will be live within 6 months. So kindly cooperate with the team, please.
Oh, excuse me?
Yes.
Did you just say the publication will be the next 6 months?
Yes, sir.
Did you just say the publication will be the next 6 months?
Yes.
Okay.
I also thank our session chair for chairing the session. Thank you for chairing the session, ma'am. This is a token of appreciation from our side. Thank you. It was great to have you here.
Thank you.
Thank you so much, ma'am. I request all the participants, just if you can just turn on your cameras for a quick snapshot, please. Thank you, everyone. Thank you. It was great to have you here. Thank you so much. Take care, everyone. Bye.